Hi, everyone. Welcome to the last session of discrete optimization talks of this semester. We are happy to start with Dr. Philipp Christophel, who's currently the technical lead for the linear programming or mixed integer linear programming solver development at SAS Institute. For the last 15 years, he has been one of the principal developers for the SAS linear and mixed integer optimization solvers, working on primal heuristics, simplex, presolver, branching, and cuts. Before SAS, he received a PhD in business computing from the DS&OR lab at the University of Paderborn and spent the summer at Core in UC Leuven. Um, with that, Philip, oh yes, and as usual, we will have breakout rooms after the both sessions, so in an hour, in which you can ask one-on-one questions or just to hang out. In the meantime, if you have any clarifying questions, please post in the chat, but they may only be fielded at the end of the talk. Again, welcome everyone. Thank you.
Yeah, welcome from me as well. So this is great because I finally get to give a talk about cuts. I've been giving talks about all kinds of mixed integer solver stuff for a while now, but I've rarely given a pure cut talk in the last 15 years. And the simple reason for that is that I don't have any good results. So now Alex said I should give a talk on cuts. So I'll talk about all the failures, which is easier for me because I got plenty of those. So the idea is that today I have this agenda here. I'll give a quick introduction to cuts. I don't think anybody needs to get explained what a MILP solver is around here or how branch and bound works. But I want to talk about cuts and my view on it a little bit. But then I have more or less 3 stories that I consider personal failures in cutting planes. But they're all, they're not total failures. And I think we can still learn some things from it. And this might be the right venue to talk about these things. So first, introduction to cuts. I like to think about cuts with this very simple example, which I think is a beautiful way to think about cuts, especially mixed integer cuts. And so this is the simple mixed integer rounding cut. This is from the book by Lawrence Woolsey, the Blue Book. And it basically says that if you have the most simple mixed integer set that you can come up with, and you can put it in a picture like here. So the feasible points are these, dark black lines. We have one continuous, one integer variable. So you don't have points. You actually have these lines as the feasible region. And for such a set, the valid inequality or the cut that cuts off this point here between 2 and 3 on the y-axis can be described with this very simple inequality that includes the fractionality of the right-hand side, and then you round up the right-hand side, you put the integer variable somewhere there, and that's your cut formula, right? And the beauty about this is, of course, you have only 2 variables. That's the simplest set you can come up with, and this very simple inequality, works. And the really great thing for me was when I realized that this is pretty much all you need in solvers these days. I mean, we have a few cuts that go beyond this, but a lot of the hard work that mixed integer programming solvers do these days is all based on this very simple kind of MRR cut. And of course, the issue that we have as solver developers with cuts in a way is that what I have here on this slide, and that's this issue that you have with papers writing about families of valid inequalities with separation algorithms and with what we actually want to have in a solver in the end, which is a cut generator. So what do I mean by this? Well, many papers talk about families of valid inequalities. So they describe a set like the simple MRR set I showed you on the earlier slide. And then they say, okay, and this is a family of valid inequalities, and they have these properties, and you can prove some things on them, and that's pretty much a paper, right? And there's plenty of these papers out there. And the issue with these papers is that typically that doesn't actually help you in solving instances. It gives great insight sometimes, and it's a good starting point. Some of these papers also give you a separation algorithm where they say, okay, we can, this separates algorithms. If you have a fractional point from an LP relaxation solution, you can plug it in here, and then you get your cut out in the end that is maximally violated or has some other properties or whatever. And they tell you, okay, this is NP hard. And maybe they give you a heuristic, but the issue with many of these papers is that they don't give you what you really want. And that is, you actually want a procedure, or, what I call, really what you want in the end is a cut generator, which is actually implementation of a separation algorithm that separates valid inequalities. And that can be all different things. So a family of valid inequalities doesn't tell you how to get a cut. And the separation algorithm might not necessarily actually be the algorithm itself, right? So there's usually a whole procedure around things. And that's why I like very much this paper by Marchand and Wolsey about the complemented mixed integer rounding cuts, because it actually starts off saying, okay, we have a procedure here that allows you to use a very simple cut formula, the one from the first slide, essentially. And we apply it together with other things. And these other things are that you convert rows to equalities, you aggregate rows together, you substitute bounds, you substitute variable bound constraints to get more integer variables into your constraint. Then you complement some variables, meaning you add upper bounds to it and stuff like that. Then you apply the formula, and then you remove all the slacks and all the other stuff, and you have the final cut. So that then is a cut procedure. And the cut procedure is very close to something you can actually implement and then get something from in the solver. People do, and this slide is just a very quick experiment I ran to give you an idea about how important cuts are these days. So on the very left of my screen here, we have the default solver at SAS, and I ran this for an hour on 1,200 problems. That's something we usually run, usual benchmarking set. And the default solves 857 of these instances. And I normalized the geometric mean of the runtimes to 1. It's 180 seconds is the geometric mean. But the interesting thing is we want to see how does the performance degrade if we turn off certain features of the solver. So if you turn off cuts, then we lose almost 30% of our performance here. It drops to 0.7, the ratio of the geometric means. So we get a lot slower. And also there's more than 100 instances we can't solve anymore within 1 hour with this simple experiment. Interestingly, if you turn off the presolver, which is another major feature of the solver, then we have an even bigger performance drop, and we also lose a few more instances. And then here in this case, the no presolver bars, they have cuts turned on again. So we always turn off one feature at a time. Of course, turning off the presolver has impact on the cuts to some degree. So it's not really a very fine-grained granular experiment, because some clique cuts will not be generated in the same way or not at all and things like that. But anyway, the presolver effect is a little bit bigger. And then the last columns here I have is basically I turned off advanced branching, choosing variables in branching based on the largest fractionality, which is the most stupid rule you can choose essentially. And it turns out that then it's even bigger. But the bottom line here is cuts are really important. They are probably, I don't know if I'll find something else that has a similar big impact on the solver if you turn it off. So especially for solving instances, cuts are crucial because there's many problems we can't solve without cuts. Okay, so that's a bit of a motivation, but now let's get into my first failure story. And that's it's become very quickly my favorite story in mixed integer programming in the last year, but that's primarily because I feature quite interestingly in it. And the story goes back to when I wrote my thesis that I finished in 2009. And in my thesis, I tried to come up with new cut generators, right? So that I was a solver guy from the start. I was never much of a mathematician. I was more of a programmer. I spent that time at Core in Belgium and, learned more about cuts. And, I thought, okay, this is great. There was this paper by Gunlick and Pochet, and they came up with this very nice simple set, again, very similar to the simple MRR set, but this time we have multiple rows. By the way, I'll have lots of formulas on these slides. I don't expect anyone to understand them. It's more like, I didn't have pretty pictures, so that was the only thing I could put up here. But it maybe gives you a flavor of what we're talking about here. Anyway, so the mixing set has multiple rows that are all one and the same continuous variable and some different integer variables. And for this simple set, you can get these valid inequalities that are put down here. Again, they will involve fractionalities of right-hand sides. They also have some sorting in them, so it's not trivially written out completely. But for the flavor, this is how these mixing inequalities look like. So Günlich and Poche came up with this. And in my thesis now, I wanted to generalize this because obviously there's not a lot of, these very simple sets don't naturally come up. What we have in a mixed integer program are rows like this, where you have some continuous variables, some integer variables, and you want to just find some path through these. So this mixed integer path that I define here is essentially just a bunch of rows. They're all equalities, and they're all connected by some continuous variables. That's really the only requirement on that. And that's not even a very strict one. So instead of having this very specific set, we want a very general set. And now we want to define valid inequalities on that. And it turns out you can define these path mixing inequalities that look terribly complicated here. It's a classic example of, it's a family of cuts. I give you this formula. I can prove it's correct. But this is only really complicated if I don't tell you how I got there. So the interesting step for this is not the formula you end up with in the end. It is the procedure that gets you there. And the procedure, that you can call it the path mixing procedure, is pretty much the same that we saw for the complemented mixed integer ironic cuts in the introduction. So you take some rows that form a path. You have to probably make them into equalities so that they form this path structure we've seen earlier. You do some aggregating. The aggregating here is different and special. You aggregate always the first k rows, and these aggregated rows, they form the mixing set that you start from. You do some bound substitution, some complementing, and then you just take the formula that Oktay and Eve came up with and apply it here, and you got some new family of cuts. Looks very complicated, but pretty straightforward. In my thesis now, I did this and I tried it out, I implemented it. And the thing is, when I implemented this, I realized very quickly, well, I should get a lot of problems solved that I couldn't solve without this, especially lot sizing problems, because the Günlich and Poche papers says and shows you clearly, oh, this will give you these cuts for all these lot sizing problems and whatnot. And it turns out when I implemented it, it didn't work. And of course, when it doesn't work, then as a PhD student, you either give up or you try harder, or you try to find out what's going on, right? Fortunately, I tried pretty hard to figure out what's going on. And the conclusion was pretty much on the upside, these path mixing cuts, they include the CMR cuts. They're generalizing it. Generalizing is typically a good thing, right? They do include a lot of lot sizing cuts. And we know lot sizing cuts are important because lot sizing problems are hard to solve without cuts. And this generator, so I had two cut generators for these cuts that have slightly different approaches in how they do things. The first and simpler one, the uncapacitated path mixing cut generator, is very easy to implement if you already have a CMR algorithm. So, there was there's some reason to say, oh, this is nice, right? Problem was, as I said, I did this and it didn't really work great. What I concluded is that, well, these path mixing cuts are not working because the complemented MIR cuts can actually generate the same inequalities in the end, because any mixing cut is just a low rank MIR cut. So if you apply CMIR on cuts you generated previously, you can theoretically get these path mixing cuts. And it turns out you practically also do. I saw it happen in my debugger. So, well, I said, bummer. I defined cuts that we already get, and we didn't know we did get them. Interesting, and I spent some time on my thesis. Some pages are filled with these things, examples and stuff, but well, not a great result. The other thing is that the flow path cut generator by Van Roy and Wolsey, that is also, a standard in most solvers these days, also generates the same cuts. Essentially, I defined some cuts that are already defined by we already get them from other algorithms we have standardly implemented everywhere. So it was a bummer. And of course, now I could say that was a big failure, but it turns out my failure back then was not that I came up with these cuts. The failure was that I didn't realize that they were still helpful. So there's an interesting tale here in a way, because a year ago, I went to Informs and I learned from Gorobi that they implemented these path mixing cuts, specifically the UPMC cuts that are very easy to implement. And it turns out that they implement them and they work great for them. And they even cited me and stuff like that. I'm like, wait, but you're citing the stuff where I basically say this doesn't work. Yeah, it's not how we read it. And it's like, well, I probably didn't write it that way because I still wanted to get a PhD. I didn't say this is all bullshit, right? But still, anyway, it was a very interesting experience for me sitting there. And of course, I came back from Informs and immediately coded up this stuff, 15 years later. And I think I found a few bugs in my formulas, just in case you try this as well at some point. But anyway, I coded it up and it immediately worked. And this is an evaluation I recently did where I said, okay, so if I take my default and I turn off the path mixing cuts, how much does it hurt? Well, it's only 9 instances we lose, but these are 9 instances we don't get otherwise, right? So in the solver world, getting an instance or not getting an, so it was surprisingly good. And even this 2.7% or something speed up doesn't sound huge, but for a single cut generator, it's surprisingly big improvement these days, right? So now the question, of course, is why did I fail to realize that this stuff works? Well, 15 years ago, we didn't have the same instances we have today. So that is a big difference. But in a way, this is a much bigger failure because I still, to the day, don't know, are these cuts really good, or what is it that makes them work now that didn't make them work back then? I actually don't know. And there's a lot worse things going on because there is this other separator, cut generator for capacitated path mixing cuts. That's also my thesis. And maybe I can make that work again as well. But so far I haven't tried very hard either. But I think there's still a lot more work to do. And the failure really is in here that sometimes you have some idea and some you believe in it and whatnot, and then you're as the normal PhD student, if you work on something very long, you're disillusioned by it after a while, and that is the perfectly normal process, I would say. I think that's that's probably the sign of good research. If you hate your research after all the time you spend with it, like 4 or 5 years, that probably means it's good because you question it continuously. But then again, it might just take another 15 years and it turns out it is good, right? That is probably the little moral of this story here. I also want to say that, people could accuse me of saying that, I'm using this resume of failures thing to promote how great my cuts are. I can promise you, I don't feel that way. It's really that this stuff works, and why it works is puzzling me. I see this as a huge failure in my career that I wrote something that works and didn't notice for 15 years. By the way, the same cuts are also in Highs, and probably that's where Gurobi got the idea to try them out. So Highs was open source, was probably the first to try this idea again, and then inspired Gurobi. So there's even a moral about open source in all of this. Anyway, I got more interesting stuff to talk about, so let's move on from that. But maybe in the breakout we can talk more about the path mixing cuts. This one is an absolutely great failure in my mathematics skills, which is which aren't great to begin with. As I said, I'm more of a software developer kind of person, and I think Alex mentioned it. I studied business computing, so I'm no math degree whatsoever. But during my thesis, I worked on these path mixing cuts. I also worked on MRR and flow cover cuts because all of these are very related. And while I looked into the lifted flow cover cuts that Gu did as part of his thesis, I think even, I also came across the mingling cuts. So the mingling cuts are this rather complicated construction you see here, and it's probably not even everything you need, but the paper is cited at the end, so you can look them up. But it's a beautiful construction because it tries to generalize some of the sequence-independent liftings that you can do for cutting planes. And it does that by having 2 nested sets and doing these formulas, where you try to find the minimum in some sequence, where you have brackets where you have to fall in between, and you can get coefficients for it and stuff like that. So it's a pretty beautiful construction, and it's a very nice idea because it generalizes these lifting things. And in the solvers, you always want to avoid having these very specialized arrows. You always prefer to have something that's more general because it might apply more often. And you're not writing code for 3 instances, you write it for maybe more, right? And so when I saw the mingling papers come out back then, I was like, oh, this is amazing. There must be some relation to these lifted flow cover inequalities that Gu defined, which look like this. I'm not giving you the full definition here. There's the function G for the C minus part, which is on the next slide. But the lifted flow cover cuts here are interesting primarily because in my thesis, I found that that is what makes the flow cover cuts better than MRR. Flow cover normally are just MRR cuts on binaries. So the separation is a little different. So the procedure is a little different. So the cut generator can generate different cuts, but they are part of the family of MRR cuts, right? But not if you add this lifting. If you add the lifting, they become something bigger and better. And that basically means we should have flow cover cuts and MRR cuts because you can get stronger cuts for your flow sets using the sequence independent lifting and using this formula. So naturally back then I thought, okay, there must be a way to show that, how the relationship between these lifted cuts and, the mingling cuts are. They try to achieve it. Maybe they are the same. Maybe you can show the lifted flow cover cuts are actually mingling cuts. And I tried. And the thing is, I tried again and again. Actually, I remember at least 3 or 4 times in the last 15 years where I got out this stack of paper that I have somewhere here. So I have this stack of paper, and I moved it across continents several times. That has handwritten notes all over, and I got to the point where I'm pretty sure mingling cuts are so lifted flow. So the simple generalized flow cover inequalities that Gu has are mingling cuts, except if you get into this one case in the function G, because I wasn't able to show that you get the same thing with mingling, which of course means I never was actually able to talk about it or publish anything about it because my result says, yeah, they're almost the same, right? It's a non-result. I think it's super interesting and it would be really great if we could somehow figure this stuff out, but I wasn't able to, right? And of course the question is, am I wrong here? Or can you easily extend the mingling cuts and then you get the lifted flow cover cuts? Maybe not. I don't know. Anyway, the final story I want to share, and I think we're good in time, that's great, is the mystery of cut selection. So, I talked about these cut generators, and in a way, I think of writing a cut generator as the easy part, because you'll typically find, you'll find some instances where your new cuts work on. In worst case, you have to create the instances yourself, but that's okay. The issue starts when you actually want to add your cuts to your solver, because the solver has to handle the cuts somehow, right? And primarily what you need to do is you have these bunch of cut generators, and by now, each solver comes with like a dozen. Clique cuts, cover cuts, gob cover cuts, Gomory cuts, 0, 1/2 cuts. I don't know. The flow cover, flow path mixing, MIR, there's all these cut generators. They all generate cuts, and they, as I kind of pointed out already, they all generate subsets or overlapping sets of the same families of cuts in the end, right? So it's worst case, they generate the same cuts. And that actually does happen. And so you have to select the cuts. So, and it's been long known that you need to select your cuts in batches and add them to the problem in chunks, always several rows together. It's also, so this kind of slide says what works. So these are the things I think I do know about cut selection. I think I know that this distance measure to evaluate how good a cut is works best. And that is also the most simple measure. Not the most simple, but one of the more simple measures. It's just normalizing the violation of the cut with the square norm of the coefficients. So basically saying if you have more coefficients and whereas the bigger, then you want to reduce the score or the violation of a cut. We know pretty much that removing similar and parallel cuts is obviously a good idea. We also know that removing cuts actually that end up being basic after a solve, obviously they can be removed. Is it better to keep them in? And it's pretty obvious that it's not. You got to be careful to add cuts in the tree. That's also pretty obvious. And you also got to limit the cut length, because long cuts, dense cuts are bad. But this is where the first time I have to use some brackets here, because that's also not always true. So limiting them, yes, but you got to do some magic as well. And that's where the thing starts. There's a lot of stuff I can also say I know that doesn't work. My former colleague Franz, who also got his PhD in Paderborn with me, he wrote a great paper about cut selection, and he had like, I don't know, 24 different cut measures. I mean, it's pages and pages of different cut measures. I think none of them actually works. I think I tried a couple. I mean, I tried a lot actually, but none of it seems to really help in selecting cuts. At least last time I tried. There's also no way to use any simple measure for cut length. You cannot just say, oh, I only want sparse cuts. Sometimes you need the long cuts. You need some complicated form of choosing what kind of cuts you want. It also doesn't work to only add the cuts in the root. It was a while ago when people talked about, cut and branch or branch and cut. Just cutting at the top of the tree is not enough. There are instances where you need to come. I mean, the biggest improvement of the bound typically happens in the root node, and that's where many instances need to be improved a lot, but it's not generally true, unfortunately. It's also not a choice to add all cuts found. One might think that might work. First, you think, why wouldn't I add the cuts? Well, the LP relaxation gets bigger, but it also gets complicated, right? So it's not just the size that grows, it's also numerical properties, and the simplex gets confused, and there's all kinds of issues if you just add all cuts. So not a choice. And then there's also this interesting question that, if the MR cut generator is so nice and it generates cuts that are very related to the original constraints, why don't you give that a higher priority over Gomori cuts, who give very weird coefficients sometimes? But in my experience, it never helps. It doesn't help to do anything. So while I said a few things that I know work and a few things that I think don't work, the true thing here is that after 15 years of working on cut selection on and off, I cannot say actually how to do it. My hope is always that, I meet someone, I do meet the people from Gurobi or from FICO or whatever and talk to them. But, if they say they are absolutely sure of how cuts should be selected, I would be dubious. Because there's sometimes you try things in this area where you try two complete opposites and both make things worse, right? And that kind of tells you that there's weird effects going on, right? And then there's the big question that actually goes beyond cut selection, which I call cut management, which talks about, this whole adding and removing of cuts, and can we specify which cuts we're going to need to solve something? Should we keep previously generated cuts or only the ones that are for the current specific LP relaxation? There's a whole lot more things you can discuss here, and it goes on and on. But let me come to a conclusion on my 3 topics here, because my clock says we're nearing the end. About the path mixing cuts, well, this revisiting an old idea is typically a good idea, and we have a long history in MILP solver development where people tried old things and suddenly they worked. So it's a proven concept. And in this case, it was really interesting for me. I'm pretty sure now one of the reasons why I did conclude that my cut generator didn't work was because I didn't have the right instances. Some instances that we can now solve, we couldn't solve because of other parts of the solver. So I had the instances back then. I did improve their bounds, but we couldn't solve them anyway. So I didn't notice that my cuts helped. And then there's a bunch of instances that we just simply added to our libraries later. So, although back then I actually, for the thesis, I had instances from a specific lot sizing problem library, but by now I would say it is perfectly fine if you work on cut generators. If you can't make it work on public instances, it's fine to create your own instances and see if they work there. That's something I would actually recommend by now. if you can make it work for your set of instances, that's fine. That's a good start. These might be the instances we want to solve at some point. But the mingling cuts, well, I don't know if my failure is just I'm not good enough with algebra. I mean, I got pretty close to proving what I want to prove, but pretty close is usually useless. So I'm very curious about this question. So if someone feels like, diving into that, maybe there is something we can do with these results and, bring them on one page eventually. And now there's my surprise for Alex, because for the cut selection, I'm really not sure what to do. And if you don't know what to do, maybe machine learning is the answer, right? Some people seem to think that. To be honest, my personal opinion is more leaning towards that we probably should just employ more basic statistics that you don't necessarily have to call AI or machine learning. Clustering cuts, or somehow identifying groups of cuts that work well together or that are similar. So you pick one of each cluster or stuff along those lines. I have not tried it very thoroughly yet. And I think it might be a way to go, but in the end, I really don't know. So quick shout out for the MILP 2024 before I finish, because if you have these instances, you generate it just so you can prove your algorithm works. There's a great way to make them public. It's the MILP 2024. So if you have instances you generated yourself for your own research project and show that your method works great on it, suddenly there's an interest in it. So especially for all the academics, all the PhD students out there, if you formulated MIP problems that are pretty much any MIP problems you formulated, submit them pretty much right now. It's still open until the end of the year. And if you really want to, I'm pretty sure Mark will accept your instances also in January, if you really can't make it before Christmas. Okay, this is the slide with the references. I'll keep it up here for the video to, people can stop here and find the paper they're interested in. And then I say thank you. And I'm looking forward to some discussions later on.
Thank you, Philip. Yes, we will have a breakout room in roughly about half an hour, where I'm sure you'll get lots of interesting questions. I think my questions will be interesting, in other words, for sure, and surely from others. Thank you very much for the wonderful talk. I'm glad that you finally have a chance to have presented some of these things that you've been thinking about for such a long time, and all your expertise is going to be very valuable for everybody who's watching here and in the future. So thank you again.
I just said I don't know anything.
Yeah, I think that's the start. Like I said, every day is a day to be curious. Okay, so I have lost my recording. Oh, there.